Well, hi everyone. My name is Fraser Kane. I'm the publisher of Universe Today, and this is your weekly space hangout for April 26, 2012. This week we're going to have a bit of a special on dark matter with a whole bunch of really interesting stories that have come up this week and last week. But we're also going to talk about some asteroid mining, and new information on Vesta, and some bit of nostalgia about the moon. So joining me this week so far is, of course, Dr. Pamela Gay, my co-host on Astronomy Cast, and a new face this week, which is Jason Major, who is a prolific journalist. He writes for Universe Today. He writes for National Geographic, for Discovery Space, and at his own blog, which is at Lights in the Dark, which is fantastic. And you've been working with us for almost a year now, Jason. So
it's actually been over a year.
Has it been over a year?
Mm-hmm.
Yeah, no, it's been great.
It's been a great year.
So it's just great to have you, and it's great to have you. We have these great conversations on the phone and on Hangouts. I'm like, oh, I got to get Jason into the Hangout. So it's great that you were able to participate this week. So let's start. I warned people about the dark matter story. So why don't we start with that? Now, last week, Pamela, you talked about I guess, a challenge to dark matter.
Yeah.
And this was, right? And so why don't we give a little history first before we move into all of the new dark matter conversations this week?
Well, people have never really liked the idea of dark matter, this strange stuff that's out there that doesn't interact with light, doesn't emit light, doesn't do any of the normal things that you expect matter to do. But it's been known for decades that there are things orbiting within our galaxy that are moving at velocities that can only be explained through having extra invisible mass out there. As we observe various galaxy clusters, we see that there's mass that can only be there's motions that can only be described with extra mass. All of these things add up. And the explanation that we've come up with for that adding up of, well, there's stuff we can't see, is we made up particle names. There's a particle out there, we're calling it dark matter, and all the evidence that we have points towards this consistent model of a diffuse particles that are basically non-collisional, non-interacting. And no one likes that. It's a theory that people love to hate. And so there's constantly theorists coming out and trying to say, oh, well, what if? So last week we saw a theory paper where people did a new set of measurements and a new set of way of doing the calculations to understand the motions of the nearest 400 stars. Now, the thing is, we can't highly accurately measure those motions. And so their new way of doing all the calculations, they say, gives us a 4 sigma ruling out of dark matter. But there's still a lot of stuff that needs to be analyzed. People need to go through their several pages of calculations, see, well, okay, does this really rule it out completely, or does it just rule out one set of motions, and what are the real errors in the measurements of the stars that went into all of these calculations? So that was last week. Well, this week we have PhD student Michael Pulowski and his professor Pavel Krupa at the University of Bonn in Germany have been very carefully surveying the region of space around the Milky Way galaxy, looking for all the small dwarf galaxies that are out there really hard to see. And the thing about dwarf galaxies, I actually did my master's thesis on the Ursa Minor dwarf spheroidal galaxy. These are systems that are so close that it just looks like an overdensity of stars on the sky, and they're so diffuse that you can just look straight through them. So if you have a large 1-degree field of view camera, when you look at this galaxy, it's just an overdensity of stars spanning the diagonal. Now, as they surveyed, carefully looking to try and identify all of these small overdensities of stars, they found a large number of these small dwarf galaxies, and that's fine. That was predicted. We knew that there should be a bunch out there. But when they found them, they seemed to all be streaming out in a tail, in one geometric strand. And the theory that we had on how galaxies and the family of dwarf galaxies around the galaxy should form is you have an overdensity of matter, and stuff just falls in from all sides. And so what Pulowski and Krupa are arguing is that because the dwarf galaxies that they found have this unique geometry Therefore, dark matter can't be true.
Yeah.
Now, this to me seems really kind of over the top of an assumption to make, because we see lots of galaxies out there that as individual galaxies through various gravitational disruptions have been stretched out into tails, have been stretched out into long filaments. We know when we look at the cosmic structure of the universe, we have these filamentary structures. So while one galaxy probably it's an unexpected result, I don't think it's enough to say, no, dark matter is dead. I think it's enough to say, wow, I wonder if we had a collision in the past that we don't know about that caused this structure. I wonder if we picked these things up somehow. There's lots of modeling, lots of scenarios, lots of things that need to be thought hard about. So they've come up with a problem. There's this filament. They haven't come out with the death nail that goes in the coffin and says dark matter isn't real, because there's still so many other things that dark matter explains. And this is just one, oh, what's that we need to work past. And it's going to be interesting to see in the coming months how people model in computers, what are the different ways you can get this structure? Are there other explanations? So these people, you have to also, I admit, they have a vested interest in killing dark matter. They have a blog called Dark Matter Crisis. They've been complaining for decades. And when you approach science with a preconceived notion of dark matter can't exist or anything else, it affects how you view your results. So I come into it with the bias of gravitational interactions create weird structures. I see something like this, and I'm like, oh, I wonder what interaction we had in the past. That's my bias. They come into it with dark matter shouldn't exist. That's their bias. Each of us as human beings bring biases to science, but as a community, we work to remove our individual biases and argue our understanding forward one computer model and observation set at a time.
And I think that, whenever we post a story on Universe Today about this, we often get a bunch of comments on the stories that are really follow a theme, which is dark matter and dark energy, which sort of have nothing to do with each other, never sit right with me. As soon as they were proposed, I didn't like them, right? But I think that, and we've had this analogy in the past, that when you want to think about dark matter, you want to think about a strange knocking sound that you hear in your car when you're driving it on the highway up a hill when you're turning right. That you're like, well, there's this weird knocking sound that's coming from my car, but the moment I started to hear it, it just never sat right with me. Right? That you can't ignore it. The fact is that, yes, there is a sound coming out of your car. Now, you might not know what it is, and you might not know what's causing it and how to make it go away, or even if it's going to wreck your car, but the reality is that that sound is there. And when you look at dark matter, we've got these situations where, and even with a lot of the more recent research with the gravitational lensing, where you can see clumps of material which isn't interacting in any way, shape, or form, but is actually clearly through the gravity lensing the mass behind it. There is something there that is interacting with the surroundings through gravity, and so now you're at the point where we've really where scientists are really defining the parameters of what this mystery is. But the mystery is there. It exists. Just because the name is weird and sounds very mysterious, there is something there that is interacting with the environment. And ideally, research like this is great. Can't find it in the local environment. That's great. It's causing strange tidal tails. Very interesting. Doesn't seem to be colliding with each other. It still interacts with gravity. You're just defining the parameters, and eventually, as with that car, the mechanic is going to be able to say, I see what it is. It's this bolt is loose, right?
And at a certain level, we really biased people towards not liking dark matter and dark energy with how we named them. Mm-hmm. Because the
sound is spooky. It's a spooky name, and it sounds sci-fi.
Right, and so people are just like, that's crazy talk, and so we gave it a name that is the name you'd give something that you want to make fun of. And in fact, there's lots of things in science where the name that stuck was a name that was originally given to mock the theory. Big Bang was a name originally given to mock the theory. Yeah. And so I think that if we, instead of calling it dark matter, called it, I don't know, we like to put words together out of things that end in on. So if we'd named it like drillions. If instead of dark matter it was drillion particles.
Yeah. Massions.
Yeah. If we gave it some sciencey sounding name, people would be like, oh, that's cool, I want to learn about it. Yeah. So we've biased the audience towards having an emotional reaction. And we have biases, we need to figure out how to get past them. We have emotions, we need to figure out how to get past them. Science is about facts. It's not about your stomach. And that's just a reality we have to understand.
And so then, as I warned people at the beginning of this episode, Jason, you've got a story that's very similar about WIMPs.
Yeah, instead of, Pamela's story was dark matter on a grand scale. That was, on the super macro level, looking at galaxies and dwarf spheroidal galaxies. That's a tough word, dwarf spheroidal galaxy. And then this story that's coming out of two researchers. One, Catherine Fries, she's a theoretical physicist at the University of Michigan, and Christopher Savage, he is another researcher at the University of Stockholm in Sweden. And what they're researching was the candidates that they believe dark matter may be made out of, and these candidates are subatomic particles called WIMPs, which stands for weakly interacting massive particles. So the particles have mass, and with that mass, these things have been around since the beginning of the universe. They're flying through the universe. They're basically passing through everything, and very rarely do they interact with stuff. But they do on occasion interact with stuff. They on occasion interact with each other, and they wanted to know what happens when these WIMPs interact with us. Literally the atoms inside our own body. Because like everything else, we're made of normal matter, we're made of baryonic matter. And if these particles are interacting with things, they could also be interacting with the nuclei within our own bodies. And what they found out was there are a lot more interactions than they thought. This was all done mathematically. They looked at the masses of WIMPs in certain ranges. And they find out that instead of an interaction between a WIMP particle, which could potentially be a dark matter particle, instead of an interaction happening once in your lifetime or once a year, they're finding out that interactions can be happening 10 times a year with heavier WIMPs and up to 100,000 times a year with less massive WIMPs. And so these particles that are flying through the universe, interacting with or having a gravitational effect on galaxies and on light and on the cosmic microwave background, which is the leftover from the Big Bang. These particles are also soaring through our bodies, literally billions every second. And as I just rambled through that, there were hundreds of billions of WIMPs, dark matter particles, potentially. That just flew through everyone here on the Hangout and everyone watching the Hangout.
And if that sounds really weird to people, don't forget that you've got neutrinos streaming from the sun pouring through your body right now as well.
All that stuff is happening. The neutrinos, the cosmic rays. We're constantly being bombarded with energy from outer space. Some of it is blocked by our atmosphere and our planet's magnetosphere, thankfully, but a lot of it isn't, and WIMPs can make it through, and they pass right through the Earth. They pass through basically most forms of matter. But on occasion, they do interact with, or at least this research is saying that they are interacting with nuclei in our bodies, and mostly it's the more massive atoms that they're interacting with. Hydrogen and water, and of course, humans being made up of mostly water. Hydrogen and oxygen. With humans being made up mostly of water, there's a lot of hydrogen and oxygen inside of our bodies, and a lot of atoms of those elements, and these WIMP particles are striking them. Of course, what's the effect of that? Probably not much. So as I did more research, I posed the question, well, what happens, because this happened on occasion out in space, what happens if these WIMPs were to strike each other within the confines of our body? what happens when WIMPs hit each other is they annihilate. So all of their mass of both particles gets released as energy. And it can be a fairly energetic reaction, and that's in fact what a project that's down at the South Pole is looking for. They're looking for these. They're looking for this energy that's being released when WIMPs interact out in galaxies, dwarf galaxies that are orbiting the Milky Way. So that's how they're trying to find dark matter. And even though they haven't quite seen it yet, they have narrowed down the range of these particles. Now they're looking at WIMPs. That also includes neutrinos. Some of these WIMPs could be, these dark matter WIMPs could be heavier neutrinos. So they're not quite, the WIMP category it's a category of particles. It's not a specific particle itself. So we're talking about possibly heavier neutrinos when we say what's striking the atoms inside of our body. If they do strike each other, which would be an extremely, extremely rare event, they can release energy, and that energy could potentially be dangerous, possibly enough to cause a cellular mutation. So that was a little bit of a disconcerting bit of information I got from the lead researcher on there. Right. But then she also stressed that that the chances of that happening are extremely, extremely low. But low isn't less than 1.
Right. Well, this is the part of the problem that we see with dark matter, right? Which is that, or that we don't see with dark matter, is that when you get these collisions, like with the bullet cluster, you get these collisions of galaxy clusters, and the dark matter doesn't seem to collide with each other and clump together in the way that regular matter and gas and dust does. So,
right.
So clearly, there's, as Pamela said, it never or rarely collides with itself. It has a very small profile. We're not really sure what that is, but
right.
But I think this is great, right? I mean, you've got these situations where the physicists are just continuing to define the characteristics that helps fulfill certain theories, and that gives the physicists and the experimenters a chance to go back, fire up the old CERN super collider, and see if they can find a particle that matches the parameters that the theorists are helping to define.
And don't forget about Fermilab. You can fire up Fermilab as well.
Sure, yeah.
And from what I hear, is they may even be looking for a fourth type of neutrino, a heavier neutrino that may end up fulfilling these prerequisites or these parameters that they're narrowing down for WIMPs, and then thus potentially the dark matter particles. Or it may be something that we haven't even found yet, and it'll get the name of whatever researcher finds it, and it'll go into the lexicon of subatomic particles. But they're narrowing down parameters, and that's what's happening right now.
And that's all we can ask for.
And what's interesting watching this is there's a standard model of particle physics which has no underlying it has to be like this, but it has all these beautiful symmetries where there's a neutrino to match each of the primary particles. So you have one to go with the electron, one to go with the muon, one to go with the tau particle. And there's just all these beautiful symmetries. And every time people try and come up with underlying theories, they keep trying to come up with a way to explain why the standard model is there. They always come up with having to make up particles. And one of the frustrations we deal with is we haven't been able to find and confirm any of the particles that they're creating to try and define physics that sits underneath the standard model. And this is another one of those cases where we know that there's probably weakly interacting massive particles out there, and it's an acronym that everyone probably wants to kill the people who came up with it, because you end up with WIMPs, and then of course there's the Macho project that's looking for massive compact halo objects. So we had this era of WIMPs and Machos were how we explain dark matter. Entirely bad set of names. But we're trying to come up with solutions, and hopefully in the next 10 years, as we build better and better instruments for our super colliders, we're either going to find these particles, or we're going to rule them out, and we're going to have to go back and figure out from scratch, okay, so we have a standard model. We don't like it. It works. And it's a very uncomfortable place to be, because we have ideas, and none of them are panning out right now.
Well, why don't we move on? We've got a couple of other stories that I wanted to discuss this week. We've got some more research on Vesta, which is really interesting with Dawn. So, Pamela, you had some information on that, right?
Mm-hmm. So the Dawn mission, it's been orbiting the giant asteroid Vesta for about 9 months now. They recently lowered its orbit so that they could get higher resolution images, and they also extended its mission so that it's going to be able to continue orbiting at this lower altitude for even longer, bringing us back even better data. And they're working on getting this publications out as rapidly as they can. And the recent set of announcements they came out with shows that Vesta is really a world not quite like anyone expected. There are places where, looking into the basically cliff faces on the edge of some of these large craters, they're able to see layering in the soils on Vesta that is very similar to looking at the layerings you see in highway cutouts as you drive down the road. And so we're realizing that this asteroid, this potato-shaped object orbiting the sun, it has many of the same geologic features that we see here on Earth in terms of differentiated soils. And we're learning more about its density profile, because one of the things that they can do with the spacecraft is, as it's orbiting, they very carefully keep track of how its velocity changes. And if you have a higher density region under the surface, the spacecraft's getting accelerated towards that higher density region, and then it slows down as it passes that higher density region, essentially getting pulled in and then slowed down before the gravity essentially lets go. And as they're mapping it out, what they're finding is that South Pole area where it's clear that Vesta probably got hit by something really big in its past. All the lighter weight materials there have been completely blown off, leaving behind this strange surface with a high density material underneath the strange surface. So we're learning about that. We're finding there are areas on Vesta where the crevices, the cracks, the craters are filled in and perfectly smooth, which really doesn't make sense. You see that when you get melt flows. You see that when you get lava. And it's not like Vesta ever had lava. It never had volcanoes. And so it's looking like these areas that are completely filled in are probably completely filled in with extremely fine particulates, extremely fine dust. So if you can imagine tapping the flour container and getting that smooth surface across the top, Vesta's been hit by asteroids so many times. It's the same thing as tapping the flour container, and all of that dust has settled down to be perfectly level relative to the gravitational pull of Vesta. And so we're picking up all these neat things, learning about the history of this giant potato that's been hit over and over through its history. And at different points, it's actually been hit so hard that its surface melted, and we're seeing what are called breccias. This is where you have this mixing of different minerals that are essentially glued together by once molten rock. It's this fabulously diverse mineralogy and this amazingly beautiful geography that the planetary theorists are having great fun trying to figure out how do you explain the way it's creased, the way it's wrinkled. And the next probably 5 to 10 years, we're just going to see breakthrough after breakthrough after breakthrough in our understanding of asteroids from the fabulous data that's coming back from this little tiny spacecraft.
And then we can mine them.
Well, we're probably not going to be mining Vesta. It's a little bit big. It's a little bit too far away.
A big bag to get around, around Vesta.
Right.
Right.
Maybe we'll mine Ceres instead. But I think this is sort of one of the big stories that broke this week. And unfortunately, as I said, the sort of 3 people who actually worked on this article specifically, none of them are here. So I know both Phil and Alan and Nancy all worked on stories about, and Ian actually all worked on stories this week about it. So we'll sort of probably go into a lot more detail next week about this. But the big announcement this week, of course, is that there's a new organization called Planetary Resources, Inc., which is made up of a bunch of fairly famous people, right? You've got Eric Schmidt and Larry Page from Google. You've got Peter
James
Diamandis,
Cameron?
James Cameron, Peter Diamandis from the X Prize, and Charles Simonyi, who's been to the space station. So you've got all these people who are coming together to create, and this is awesome, a company to mine asteroids.
And what I love is the graphics associated with this. They're basically building funnels to grab the asteroids and then
like baggies. They're
them.
gonna
Yeah,
put
it's
a
a
baggie
giant
around
baggie.
this thing, zip it up, and bring them back.
Yeah, yeah.
So,
And this is not that crazy. I mean,
no.
the idea, there's a great book that came out up in the 80s, I think it was called Mining in the Sky, and sort of went into what's in these asteroids. And so if you bring back a fairly small asteroid, nothing bigger than maybe 100 meters across, you've got as much of the important, the expensive things, platinum, rubidium, iridium, these really expensive minerals, more than has ever been mined in the entire Earth in the history of all of our mining. And so any one asteroid could be worth trillions of dollars. And so if you can get up there, find a small asteroid that's got a lot of that metal, you can bring it into an orbit that's close to the Earth, and then you can build the facilities on that asteroid and start tearing it apart. You could theoretically make a profit from this endeavor. This is the least crazy idea that's been out there to how human beings are going to get out and explore space. And so in the last week and over this next couple of weeks, they've been sort of gone public with what their plans are, what the team is, and put together some presentations on some of their ideas and their methodology. And it's going to be starting with just finding the right asteroid, finding the candidate asteroids.
And just that, the way they're planning to do it is awesome.
Yeah.
And it sometimes makes me worry a little bit for some of our commercial and not commercial, some of our academic endeavors. So the scientific community, in combination with a lot of national defense organizations, have been putting funding into things like the Pan-STARRS telescope, the Linear telescope, and they're working on building the Large Synoptic Survey telescope. And one of the goals behind these telescopes is to find all the potentially life-destroying asteroids that exist. And all of these are ground-based telescopes. They're fabulous telescopes. But these folks that are looking to mine, they're planning to simply launch private telescopes. So they're going to put into orbit their own space telescopes for the purposes of finding something they can go and dig up. And it just starts making me think, okay, so if we have basically the mining industry launching space telescopes to find asteroids, and they're going to be looking for the ones that come near Earth as well, because those are the ones that it takes the least amount of fuel to mine and get the resources back to Earth. It starts making me wonder, do we have to worry about they're going to discontinue funding for some of our big projects? So it's going to be interesting to see the consequences of these missions, where it's gone from being a national defense initiative to find Earth-crossing asteroids to being a national resources initiative to find and make a profit out of these Earth-crossing asteroids.
On the other hand, there's the option, there's the opportunity to perhaps partner up. So I mean, it's kind of a double-edged sword there.
Yeah, it's going to be interesting to see how it plays out, and I'm looking forward to trying to catch one of the Large Synoptic Survey telescope folks and ask what they think about these space telescopes getting dedicated to finding asteroids.
Well, I mean, this is one of the great challenges and one of the great dangers for humanity, is the off possibility that some asteroid is going to impact us. I mean, again, as we always say, it's not a question of if it's going to happen, it's just a matter of when.
Yeah.
At some point, an asteroid is going to strike the Earth, and it's going to cause a bad day. It happened to Tunguska back in, 1908.
Yeah, that wasn't really a bad day in the grand scheme of things.
If it had hit Paris.
If it had hit Paris,
if it hit
but
Moscow,
the actual almost impact was
right.
it flattened forest in Siberia.
We just got lucky.
We got lucky.
Yeah. Yeah,
and
so the point being that our luck is going to run out in the future, inevitably.
Yeah,
and
no, that's
so one of the great causes that science can do, I think, is to accurately map out all of the dangerous asteroids to a very high degree. And I think that this has been a challenge, and this has been really difficult for the folks at NASA and some of the scientific communities to pull together the financing for this goal. And we've reported on this on Universe Today, talking about these different ideas, like a space-based survey, a ground-based survey. Yeah. They've already identified all of the big global killers, and in theory now there's no risk of the one that's going to destroy, another
No, but you do have to
one's
worry
gonna
about
kill
the one that
everybody.
hits off of the coast of Europe. I mean, imagine one that nails the Mediterranean, causes a tsunami that wipes out all the coastal cities that surround the Mediterranean. You can lose Alexandria, you can lose Venice, Rome. Name a cruise port in the Mediterranean, it's gone if you get an asteroid that hits in the Mediterranean and creates a big enough splash.
Or even hits some off in the middle of nowhere plot of land. I mean, except for the not to mention the damage to the ecology there, but it kicks up all that. It kicks up all that dust.
Yeah, well, that might help with global warming.
That's true too.
Great.
Pull them in.
But right, and so I guess the point being, of course, that if you as the nice side effect of finding all of the asteroids that you can mine to make lots of money, you will identify all of the potentially destructive asteroids in our environment, and then use that same technology that you're using to move them into good places to mine. You can use that same technology to move the dangerous ones away. In theory, there's a real benefit to being able to do this, and I think that as long as this process is moving forward, I can just imagine, in a few years, you're going to be writing grants to mining companies to use their.
Okay, that's not me. That's somebody else. But yeah.
Yeah, someone will. Some scientists will be. That's the way. That's who you have to write to if you want to get access to telescope time. Is mining companies. But if it's more telescopes, it's more telescopes. So I'm not really.
That's what I'm hoping. The only concern is that the Large Synoptic Survey Telescope is going to do fabulous science in addition to discovering all of these asteroids, and you have to worry that if it somehow loses its justification because the mining companies are looking for asteroids and taking care of the problem for us, that ability to do all that science is going to go away, and the mining companies are so narrow focused. Like I said, it's something. It's interesting to see how it's going to play out. But we'd said we were going to discuss this in detail next week. So
right. I can't help myself.
Closing the door.
No, you can't. I get to still decide. I can still talk about this because I'm so excited. Anyway, we'll bring on a whole bunch of experts next week, and we will go into it in great depth. I think we may even dedicate a whole episode to it because it's so interesting and feels. I mean, again, this is the conversation that we've been having, that a lot of people are really depressed at all of the cuts that are happening in the various programs. But this is the most exciting time in space exploration that I've ever experienced.
We're just changing the emphasis. It's no longer NASA. It's now all the guys with the big bucks looking to make space profitable. We turned that corner. It's gone from Ferdinand and Isabella paying for Columbus to find America to the West Indian Trading Company trading away and making a fortune. We're now getting ready to make that switch from government-funded exploration to corporate-funded profitability. Yeah, with what Virgin Galactic's doing, what these guys are doing, what SpaceX is doing, even the real interesting stuff that's happening from China and India and Russia. It's a really great time for space exploration. So don't be sad. It's going to be cool. All right, well, so Jason, just to wrap this up, you've got one more kind of nostalgic story about space exploration days of yore. Sure. I mean, this is kind of a warm and fuzzy that I came across a few days ago. Actually, it was over this weekend because, as you may know, this past weekend was the 40th anniversary of the Apollo 16 mission, when John Young and Charlie Duke were roving around the moon and exploring the Descartes Highlands. And I found a photo that I had no idea existed. It was on the excellent site, the Project Apollo Image Library, Image Archive, and it showed it was basically a little family portrait, like a wallet-sized photo in a little plastic bag, and it was sitting there on the gray, dusty lunar surface with an astronaut boot print right in front of it. And there was maybe about 3 photos that went along with it, different angles and whatever. And I saw that and I said, oh, interesting little headline that went on, or a description. It was the Duke family photo. And when I did some more research on it, I found out that during the third EVA of the mission, right before they were setting up it was, I think, a solar wind experiment, Charlie Duke takes out a photo that he had wrapped in plastic,
brought with him to the moon, had it in his astronaut space suit, lays it on the surface, takes a picture with his Hasselblad, and then just left it there. Went along with his mission, and I mean, it's right now sitting up there on the surface of the moon is an astronaut's family photo. Looks like it was Charlie, his wife Dorothy, and their two sons. I think it was Charles and James, and looks like they're sitting on a bench in the summertime. I mean, it's just a regular family photo taken from the early 70s, late 60s, whenever it happened to be taken. And right now it's sitting up there on the moon. And I think that's fantastic. I mean, it's just like the Apollo missions were a testament to what humans can achieve in human endeavor and technology and all of that stuff. That little photo sums up the human nature that went along with it. The guy in a suit that risked everything to go there. That it surpasses so much. The rocket launches and the aerodynamics and all of that stuff gets surpassed by this little family photo in a plastic bag that's sitting on the surface of the moon. I thought that was fantastic, so I put an article up on Universe Today about it because I didn't know about it, and I assumed that hey, at least someone else out there doesn't know about it. So
yeah, you have to wonder what other random stuff has been left on the moon,
sure.
And when we finally get back there, it's been over 40 years, and so like that poor photo that's been left out in the sun for 40 years.
Oh, it's faded beyond recognition.
Yeah, it's faded. So we're going to basically be, well, not us, but future astronauts, cosmonauts, taikonauts, whoever they are going to be wandering around on the moon, picking up blasted by UV radiation beyond recognition small objects and going, what was this? And we're going to essentially be, within just 1-2 generations, archaeologists trying to make sense of our own history of leaving random stuff on the moon. And golf balls and so many other things. And yeah, it's touching and poignant, and then it's going to confuse the tar out of somebody. And I just love the extra, it's going to confuse someone someday part.
Have you ever seen the Futurama? I think it's like the second episode of Futurama where they go to the moon, and now it's a theme park on the moon, and it's kind of lame, but Fry convinces them to go out and actually explore the real moon, and they run across the old Apollo 11 landing site, and then they sort of wait out inside the lander until the temperature increases. But it's that same feeling of nostalgia, you know, that it's a museum piece sitting there on the moon. But the point being that you can actually visit it. I mean, this is all right now completely inaccessible, and so I really can't wait until we can all go back. And so we will go back. And after we've mined that asteroid, we'll have enough money to go back to the moon. So,
well, what's going to be interesting is they're going to be protecting the astronaut footprints the way they protect dinosaur footprints, but it's way harder because astronaut footprints are made out of dust.
Yeah.
Yeah, so it's going to be interesting to see how they figure out how to preserve everything.
All right, well, why don't we get in and see if anyone has any questions or comments or sort of additions to the stories that we've talked about today. So if you're watching this right now and you want to give us some feedback, you can post a comment. You can either post a comment if you're watching it on Google+. You can just add your comment to the Google+ where you're actually watching this feed live. If you're watching this on YouTube, there's a way that you can just post it into the live feed, and I see a bunch of hi from various places: Belgium, Poland, Argentina, which is awesome. It's a whole new group of people watching us. And then if you're watching it on CosmoQuest, you can also you can use Twitter, you can use the EQX and the hashtag Hangout, and then we'll be able to read it over there as well. So a couple of things that we see so far. One is John McKinney commented about the asteroid mining. He says as soon as a huge source of rare metal is found, prices would collapse.
Yeah.
This happened in the past when it's discovered how to cheaply produce aluminum. And that's a really good point, which is if it gets so cheap that you can actually pull, platinum out of these asteroids and just it's all over the place, then it absolutely would collapse the prices. But I don't think we're at the point where it's going to be that cheap. I mean,
no.
We're looking at tens of billions of dollars to even put together a mission.
And at a certain level, the things that get mined aren't necessarily going to get brought to the surface of the planet. A significant portion, I suspect, will get repurposed into building things on orbit, building things on the moon. So, yeah, there's the potential that we're going to get additional metals that don't exist on the planet, but they're going to be expensive, and a lot of them are going to stay off-surface, off-world, I guess.
Mark Barrand asks, how would you return the metals you mine from an asteroid to Earth? And this is, I mean, the risks involved in actually parking an asteroid next to Earth that could wipe out a city and then digging off the minerals from it.
So in an ideal situation, I'm not sure you'd necessarily want to bring an entire asteroid back to orbit our planet.
It'll be safe. It's safe. Don't worry about it. Don't worry about that city-killing asteroid up there in a descending orbit.
But what you can feasibly think about doing is adjusting its orbit so that it has a Earth-crossing orbit that crosses in such a way that it doesn't cross into the planet, and gets it close enough to Earth that you have a low energy dumping of materials from the asteroid to Earth orbit, and you bring a rocket load at a time, essentially.
From what I understand, a lot of the stuff may not even need to come back to the Earth's surface. A lot of it will actually stay in space for them to build and develop things there that are just too expensive or cost prohibitive to bring from the surface to space. They have it already there.
Well, and one of the interesting things to think through on this one is, if you've ever read the book The Sparrow, which is the saddest, most poignant book that involves an asteroid that I've ever encountered, one thing to consider is you mine out the core of the asteroid, turn the sucker into a spaceship, and now you have a steerable spaceship that the walls are made of rock that protects you from radiation. So the idea of mining an asteroid, this is perhaps one of the most completely usable objects you can grab, is as long as you grab one that's solid. One of the concerns is some of the asteroids that are out there are basically rubble piles held together gravitationally. And you try and hollow out a rubble pile, and it's like trying to dig a tunnel in sand. It just collapses back in on itself. So you have to choose wisely when you're picking your asteroid to dig around inside.
But again, my mind is just expanding at even though we're not going to bring it back to Earth. We're going to use it to build more spaceships and space stations and objects in space, which is, there's no need to bring it back to Earth because we're now a spacefaring civilization. So I love that idea.
The real trick is figuring out how to get the oxygen to the asteroid.
Yes. Yeah. Well, and that's where Earth. We still need Earth for something.
Yeah.
If the asteroid is full of water, water ice, there's your oxygen.
And that's tricky. So far, we're not finding that. That's tricky. We're going to have to see what Dawn figures out as it goes from Vesta to Sirius, because Sirius is beyond the freeze line. So maybe there's water out there.
Matt Milne mentions there's a Larry Niven science fiction story where they hollowed out an iron-nickel asteroid with a black hole.
Yeah, no, that's not going to happen.
Well, yeah,
great story, not going to happen.
Yeah. No, there's another great Larry Niven story, I think it was, where they're on, I think on the moon, and they find this little alien microscopic black hole, and they accidentally drop it into the center of the moon.
That's fine.
Black hole mining. Maybe that's what Zuckerberg's working on.
right. That's the competition. But the point being, you would use a black hole to hollow out something, but if it's hard to hold a black hole, and so the terrible realization in the story was that this black hole was going to be gobbling out the interior of the moon and eventually collapse the moon in on itself, and then we would just have a black hole as a moon.
But Jason makes a great point. Zuckerberg's like the one internet billionaire that's not out there building a space agency. Yeah, so we need to get him out there building a space agency too.
Well, I mean, Zuckerberg, that's crazy. Now, Jeff Bezos, of course, is already doing that with Blue Origin. So you've got these all these various people. You got Elon Musk doing SpaceX. You've got. I love it. This is so great. You've got all of these internet entrepreneurs who are as into space as we all are. More so, I would say.
They all wanted a rocket car future, and they're solving the problem with money.
And they solved the problem. Yeah. Well, if NASA can't do it, we'll go make billions of dollars, and then we'll create a spacefaring civilization. This is awesome. I love it. Yeah, and that makes complete and total sense to me. Yeah. Right? Sure, yeah.
Yeah, I'm fine with not taxing the billionaires if they're going to build space agencies.
Yeah, exactly. So I think that's good. Just a couple more questions that we might go into. Yeah. Mark commented again that asteroid spaceships reminds you of making a canoe out of a hollowed-out tree, right?
Yeah, that's entirely true.
The same methodology.
Yeah.
John McKinney earlier on in the conversation, we were talking about dark matter, and he says he assumes that the dark energy has nothing to do with dark matter, but it's an unfortunate choice of names.
It is.
And I know that was your fault, Pamela, right?
Yeah. So dark energy is the bad word choice that we came up with to describe a phenomena where when we look out across the universe, we see space. We knew it was expanding, but the rate at which it's expanding is getting faster and faster and faster over time. And the way that it's getting faster can be explained if every cubic meter of space has a force in it that is pushing out. And it's the amount of energy equivalent to just a few protons per cubic meter. So it's not that much, but the creepy part about it is, as the universe gets bigger, this stuff doesn't dilute. It's there through all of time at a fairly consistent density. And so it's like there's this background field, there's this background pressure, this background force. Call it what you will, there's something pushing the universe apart. And since it's a energy that we can't identify the source of, someone got the neat bad idea to call it dark energy. So apparently the in thing to do in astronomy, if you're a cool kid, is when you can't identify something, you take an aspect of it, matter, energy, and then you put the word dark in front of it. In the past, we've had dark stars. Later they went on to be called black holes. We've had dark galaxies, gone on to be called dark matter galaxies or low surface brightness galaxies, depending on what paper called it a dark galaxy. It's a bad habit we need to break.
Yeah, and the problem is the two now are synonymous. I mean, people will say dark matter, dark energy, when it appears that they have nothing to do with each other.
Absolutely nothing to do with each other.
Except that they're the two largest constituents of the
universe.
They're
the dominant constituents of the universe. We don't know what they are. They're badly named, but that doesn't mean they're
we only know what like 2% of the universe is. So anyway, I think we're starting to 4%, right? I think we're starting to go into ranting land. So anyway, why don't we wrap this up? So again, thank you very much, Pamela and Jason, for joining us. It was great. I see some people saying that Jason was a great addition to the team. So Jason, you're invited back every week. It's an open invite.
Oh, be a pleasure.
Now, and again, if people want to see more of stuff, they can go and check out, of course, AstronomyCast, which is the podcast that Pamela and I record every week, astronomycast.com, and you can subscribe to it on iTunes. And Jason, your blog, Lights in the Dark?
Lights in the Dark, lightsinthedark.com. Yes, I have mostly solar system information there, but you can go and see the photo that Charlie Duke left on the moon during Apollo 16. And if you want to find out more about the dark matter WIMPs hitting the human body, check out the head blog on National Geographic News Online.com. I think it's news.nationalgeographic.com, and if you don't see it there, it'll be under Space Tech.
Right.
And if you want to keep track of all the things that we're doing, you can sign up for our newsletter. Go to cosmoquest.org, register an account, and when you register the account, one of the options is to sign up for a newsletter. They go out every Sunday at North America time. It's going to be Monday morning if you're in Indonesia or Southeast Asia, or Australia, pick your place, Far East. And you can also sign up for alerts. And in the future, what we're looking to do is start sending out an email blast an hour or so before we start these Hangouts to make sure you know what's going on. We have a calendar of events. And we offer you the chance to do science and help us discover our universe. So go and participate. We're currently running a 1,000,000 crater challenge. So help us mark 1,000,000 craters on the moon and illuminate our scientific understanding before the full moon comes on May 5th.
And the next fun thing that we're going to be doing is we've got our virtual star party, which is going to be on Sunday night, starting around 8:30-ish when it gets dark. It's getting dark.
So it'll
later,
probably be 11:30 Eastern, 8:30 Pacific, way too late at night if you're in Europe. And we welcome those of you eating breakfast in the Pacific Rim.
Pamela, the May 5th moon, that's going to be a supermoon, right?
That is something.
I think it is. I think it's another one of those supermoons.
So super understanding for the supermoon. I think I can get behind that.
Yeah.
Awesome.
Yeah, no, actually, there's a beautiful crescent moon was out last night, and so I think we're going to get the moon in the star party, which is always a treat. So, all right, great. Well, thanks everybody. Thanks for watching, and we will see everybody next week or somewhere here on all of the hangouts that we're doing here on Google Plus and on cosmoquest.org. Thanks, guys, for joining us, and we'll see everyone next time.
Our pleasure.
Thank you.
Bye-bye.